Look at that. Beautiful. Beautiful. So that's our single slit interference. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.
It seems as though the more effort I put into a video, well, it doesn't hurt when I put an effort into a video. They do well. But if I were to just make a video of me turning pages, for example, somehow that does really, really well. So today, we are just going in like this. This is the preferred. If this is the preferred method of learning, this is how we will do it. Off the cuff. Inductive proof of mathematics, done properly. The problem with other inductive mathematical channels or series is that they're not very inductive. They will use six-fingered AI abominations in order to change the history of mathematics in order to explain how mathematics was invented. But was mathematics invented? Was mathematics discovered? Invented? What would you say about language? Was language invented or discovered? When it comes to concepts, are concepts discovered or invented? What about art? Is a picture that we draw of an animal discovered or invented? Mathematics is neither discovered nor invented, in the same way that neither language nor art is invented nor discovered. Mathematics, like language and art, is a representation of reality. Because these other channels are not inductive, they take about 5 months to reach multiplication, division, and fractions. This is because they are investigating whether the words match. At the very beginning, they take one set of examples, set that equal to words, and from there, they have to check if new words represent old words. They must check to see if 7 equals 7, if that new 7 has all of the features of the old 7, as if that old 7 was some object, and this new 7 is another object that needs to be compared, as if they were not equal, identical concepts. Real induction takes a little bit of autism. So, here's my autism. Let's just finish this. So, here will be my autistic inductions of mathematical arithmetic, which will be done in one video, which is apparently about 5 months of work to some others. Induction is integrating observed facts of reality into a concept, which requires an implicit or perceptual measurement of similarities which are objectively observable. For instance, here is about 1/100th of my rock collection. See how they differ. See how they are similar. This is how you do mathematics inductively. See this autistic layout? This is how it's done. We can find patterns in this. And that's how it was done old school style. So, here's what we're going to do. So these are my nice pretty rocks. And I have them all lined up because I'm autistic. But that instantly, to me, has given me a pattern. See, I can, in laying them out, one by one like this, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 22 rocks this way. 1, 2, 3, 4, 5, 6, 7. I'm going to count just to there because these guys are big. 7 and 22. Look at all the rocks I filled that space. How many is that? Well, actually, that is 22 times 7. Look, we already reached multiplication. The first minute. Just by laying out rocks, I have multiplication. In fact, if I cut this in half and were to give you half of the rocks, I would have division. How did I get these rocks? One at a time. I added them up. If somebody steals one, that's subtraction. I'll be right back. This is how you do mathematics inductively. See? We have here one rock. You can put it right here. 2 rock. You put it right there. 3 rock. Put it right there. 4 rock. Put it right there. Let's just stop right there for a second. I have 2 piles of rocks. Your pile and my pile. Which pile is bigger? Obviously mine. It takes up way more spaces than yours does. Pretty obvious. You also have collected them 1, 2, 3, 4, one at a time. There's 1, there's 1, there's 1, there's 1. But together, there's 4. This doesn't. Let's turn to the whiteboard over here. We have 1 rock, and then another rock, and then another rock, and another rock. 1, 1, 1, 1. If we want to call that something, that's not how you do that. If we want to call this a new thing, we can call it anything we want. 4, or we could call it IV, or we could call it scribble scribble. Doesn't really matter. Once you pick any label to represent the objects, you're good. You would never need, say, if you were to say that this equals this symbol, you would never then need to see if that symbol works. So if you went that plus this symbol, you went this plus this symbol, you would never need to waste an entire video proving this unless you were being rationalistic. Because you're saying that, oh, well, I don't know if this object matches this object, and if this object matches that object. These are not objects. These are concepts. And the concepts are right here. The objects belong on the table. That's 4. That's 3. It doesn't matter what you call them. You put this pile together, and you put this pile together, and you put them in one big pile. It's the same thing. Does that make sense? 7, 7. Same thing. No need to waste a video checking to see if your math works because you changed the words. That would be rationalistic. So let's explain some objectivism here. These rocks also explain objectivism. For instance, here is about 1/100th of my rock collection. As you can see, they differ greatly. No 2 rocks are similar. They are so very different that each one has their own objective characteristics. In a world where, say, this rock and this rock are the only 2 objects that exist, they would be very different from each other. This rock and this rock are different sizes, shapes, even colors. However, the moment you introduce another rock of a different type, suddenly these 2 are almost identical compared to another. Introduce yet another different one, and they become even more similar. The similarity that human beings see, the similarity that any animal, in fact, would see between these 2 and these 2, comes from the fact that these ones share a closer resemblance in color and size, and even the elements that make them up, whereas these ones are different from the others. So, similarity, you take these ones back away, let's say, put these over here, where do my rocks go? Now, back to being just these two, they're quite different. But now, because we're humans and we have memory, we're stuck with the similarities. And so we may name them. I don't know what the names of these ones are. They're covered in stuff. So, we can classify these. That is what concept formation allows us to do. We can see which ones are similar. See, these ones look similar compared to the rest of them. Can we find some more similarities? Let's see, yeah. So like this one, and 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 this one. Ooh, look at this. And this one, and this one are similar compared to these. That is Objectivism, kind of 101. We see similarities because they interact with our bodies in a certain way that allows us to see them in a certain way compared to the others. Look at this one. Very pretty. Make sense? Obviously. Of course it does. You're not stupid. So, the next step. Where do these rocks come from? They came from all over the place. But they came one at a time. Let's just move this. So, beautiful. I acquire them one at a time. 1, 2, 3, 4, 5. Stop there for a moment. No, you know what? Let's keep going. 6, 7, 8, 9. Actually, now we stop. Because now when I look at it, my brain has to, especially maybe because I'm dyslexic, I go, there are 1, 2, 3, I see 5, and then I have to count 6, 7, 8. I started losing count. That's called the crow epistemology. Settle down. The crow epistemology is such that your brain, perceptually, likes to look at things in little groups and say, if your perception is looking at these and these, let's just do it like that. That you should be able to do instantly. Because your brain kind of lumps how it sees things. So there should be a circle, 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 and they overlap in your retina. So one lumping is seeing this group, one lump sees this group, another sees this group, and then you kind of report 4, 4, 1. And if you're really good at math, 4, 4, 1 is 9. Your brain, however, when you put them back together, sees this lump of maybe 4 or 5, and this lump of maybe 4 or 5, and it goes 5, 5, 4, 4, 5, and it struggles. So you have to take a moment and kind of count. If you have only a select few, it doesn't really matter how you arrange it. Your brain sees that lump as that lump. But once you exceed your crow epistemology, everyone's got slightly different, then it starts getting a little confusing. So, what you can do for yourself is you just start another row. You see that? And now we're going 1 to 1. This other row. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 here, 9 here. 2 rows of 9. Settle down. There are 9 here. From here to here. And there are 2 here. If we add those up, 18, or 9 times 2, 18. Our concept of multiplication is simply how many groups of how many numbers. Our symbols for that don't matter. Once you've picked how many they are, I don't care if you call it 9 or 9 or nouveau. Spanish, help me out. So, if we then cut this in half, 18 was our total, divided in half is 9. Look at us go. We are flying through this. So, if you line them up one at a time, that's addition. 1, 1, 1, 1, 1, 1, 1, 1, 1. And you give them a name. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9. That's 9. Anytime we have anything of this many, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9. Right? Easy. Easy peasy. Okay. Here we have a pattern. A triangle. We can in fact see that there is a triangle of rocks with a smaller triangle of rocks inside, and in fact there is a negative space which also makes up a triangle. This is just a pattern that we see in real life. We can line things up. In fact, let's do another pattern here. Do 4 this way, 4 this way, 4 this way. Guess how many rocks it will take us to go back to the beginning. 1, 2, 3, 4. We got ourselves a square. If we were to cut the square in half, we could put these here, and we get a triangle. Wowee! It's as if arithmetic were really easy. So, alright, see here, we have a pattern. We have a triangle. There's this many rocks outside, a set of rocks inside, and you can even count the number of internal spaces, which also make up little triangles. If we were to fill this space out, Blamo, look, we got a square. Look at this, we're doing geometry. So, this is how inductive geometry and mathematics really are. We're just playing with rocks. You just gotta have enough autism to collect enough rocks and find fun in playing with them. That's where mathematics, that's the heart of mathematics. Right there. The heart of mathematics is being autistic and seeking patterns. I'm sorry for neurotypicals. Da, da, da. Right there. Bam. Patterns. So, what do we have here? We have squares, a concept which is an equal a number here as here. So let's do our big square. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 on the top and the bottom. That's what makes them parallel. We can prove that. Want to prove it? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Proved. Check. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Look at that. 11 and 11. We got ourselves a square. If I wanted to know how many rocks fill this space, well, I can just count them by filling them up. See? If you have enough rocks, you can do anything. Okay? Take that lesson home with you. Look at me go. So many rocks. Okay, do I have them? Does each space have a rock? It looks like it. So we have a situation where we are really autistic and we have a lot of rocks. Okay? This is why mathematics was invented. Because first, you find a bunch of pretty rocks and you take them home. And then you have a bunch of them. And in order to look at them all, because there's too many of them, you have to arrange them by spacing them out. And when you space them out, you discover patterns. Right? This is why mathematics and autism are related. So we counted 11 actually on the bottom. Let's just be really stringent about. Let's work hard. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 on the bottom. This row, there's 11 in this row. And then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 rows. Voila! 11 rows. And if we keep counting, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have another 11. Now, we could do it again. We could. But see, the point of mathematics is it's neither invented nor discovered. The concept of 11 is a concept. That's invented. This symbol, which can be written as 11, or it can be written in a different language, represents the same thing. It's a concept, but the number 11 has a similarity such that if we were to set them one by one, the pattern will be that the same number appears. That is the concept of our square. A square is another concept. It is this concept. It is this picture put into words, put into concepts. This observable fact of reality, integrated by the fact that I could draw a digital one here. You can make a little square out of these observable facts. The observable fact that it's a one-to-one relationship along here and along here. Square. 11, 11. It's observable. I don't need to think about it. I can see it. And then there's 11 of them, and 11, 11. And that's not a square anymore, but that was... So we had 11 going this way, and 11 going that way. And we can count them. Because 11 times 11 is another way of just saying square. That's just a concept. This is a concept. Timesing times 11 times 11 is another way of just thinking about squares. Okay? And that concept is the same as 11 plus itself 11 times. 11 groups of 11s. 11 groups of 11. Right? So we can count it. 11, 22, 33, 44, 55, 66, 77, 88, 99, 100. Jeez, that's loud. Is that a helicopter? $100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 121. You can see them. This is what 121 looks like. It looks like 11 by 11. Now, we play. Let's make half. What is half? Well, half would be if we took from the dividing line look at that. So, these ones, do they count? That's a question that we need to turn to something else. Or we just count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. 1, 2, 1. That's fun. You want to talk about patterns? That's a fun pattern. Let's look at that. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11. What does that equal? What do you think? Well, if you went 11 plus 1, that would equal 12. And if you went 10 plus 2, that would equal 12. Oops. Whoop, whoop. Let's keep going. 9 plus 3, 12. 8 plus 4, 12. 7 plus 6, 12. Wait, what? 6 plus 5. That's not right. 6 plus 5. 12. 6 plus 6. 12. Okay. 1, 2, 3, 4, 5, 6. There are 6 groups of 12. Isn't that interesting? So what is that? Well, 6 times 10, 60. 6 times 2, 12, 72. So, 121. Let's check this. Half of that, 6. Can't do that. 60.5. We get 72. So, what's going on? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's go 72 minus 11 is 61. Just up this much. So, that's kind of the difference between a discrete mathematics and a smooth mathematics. So if we wanted to actually make it, say, fully even, maybe we would just need the right size rocks. But we're getting, because this was being counted twice, if you remove them, we have the proper amount.
The inductions of mathematics do not require inventing. Mathematics is a language which is describing. It describes the quantity of something. It could be the quantity of their colors, which we could rank by some number, and then we could arrange them by that number. Or we can just take the quantity of how many units there are. But it's just a description of what is present. So the inductions of mathematics would be that to add would be to take one object and put it next to another object. And we give them names. 1, 2. So together, there's 2. Separate, they both would represent 1. The concept of 1 represents. The concept is the observable fact of reality of this singularityness as compared to this non-singularityness. these guys are by themselves. In our human minds, we can even say these two, flip it over here, these two have escaped from their pile. Because we are tying these ones together. The inductions of mathematics should not take 5 months to complete. It's a very simple process, especially when you're autistic and you have a house full of rocks that you might like to organize. In such activities, to take from a pile is to subtract one from the pile and to add it to our display. Subtract one from the pile, add it to the display. Take one from the pile, add it to the display. The piles, in fact, were already divided in half. Look, bacon. Little bacon rock. Add to the pile. Concept formation is to take similarities. These guys have been separated from the piles. We could count them individually as having 1, 1, 1, 1 escape the pile. Or you can count them together and give it a new concept, which represents how many there are. 1, 2, 3, 4. We could represent them with other objects. 1, 2, 3, 4. The objects are quite different. However, the quantity is the same. Once you've established that concept, you do not need to reassure yourself that 7 equals 7. The induction of addition is actually just the process of counting, where we give it a symbol for each time we add 1. That is the concept of counting. The concept is to, and it doesn't have to be by 1, to count you can count by 2s. 2, 4, 6, 8, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can count by 2s because you can count by 1. It's implicit. It's objective. You don't really need to explain it. I don't know why it takes some people five months. So in order to add, one just needs to count. We give a symbol. I'll just put a little digital symbol. 1. Call that 2. 3, 4, 5, 6, 7, 8, 9. If I put another, we get 10. 10 is where we repeat ourselves because, look at that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we were to put our fingers on these spaces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look, we take up the same amount of spaces. Wow! That would take someone a whole video. So, we keep moving on. If we were to have this many, this is 10. If we divide it in half, we could also have subtracted by 5, whoa, language. The introduction of language into mathematics. That is our inductive process. It shouldn't take someone 5 months to do this. I'm going to keep reiterating that. So, to divide something in half is to take an equal amount. And so you could also have subtracted that amount. Right? You can also then add that back on, or we can multiply it. Multiplying it would be to have that many groups of it that many times. This would be the result of multiplying, because there's 5 by 5, 5 groups of 5. That's what it means to multiply. It means to make groups of. Multiplying in its simplest form is to make groups of 1. 1, 2, 3, 4, 5. One group, 5 times, equals 5. If you did that again, you'd get another 5. You did that again, you get another 5. You did that again, you get another 5. And yet, one more time, you'd get another 5. 5, 10, 15, 20, 25. Multiplication, division, addition, subtraction. Fractions, actually. Look, 1 out of the whole lot, one group here, out of the whole lot, that is a fraction. I'm going to just put some digital circles here. We take these 5, and we make a little circle around them. Make a big circle around the rest. Small circle out of the big circle, 5 out of 25. That would be the same as, well, we can take 1 out of each group, but when we do that, we have to take 5 out of this group. We need to take it 1, 2, 3, 4, 5. Actually, take 4 out because he's part of the group. He's a part of the group. Don't mess that up. He's a part of the group. So these guys then lose another 4, and he loses another 1. They should lose another 4. He should lose another 1. They lose another 4, and he loses another 1. And look, 1 out of 4. Ha ha ha! Because we can then pair these back up. Woohoo! Whoops! Explosion. Where did you come from? What the hell? Yeah. 1, 2, 3, 4, 5. Good. We can count. Look at that. So that's 5. 1 out of 1, 2, 3, 4. Look at that. Another set where it's a representation of 4 to 1. And so then if you take 1 out of this one, you'd have to take 1 out of each one of these guys. Take 1 of it out of here, and you have to take 1 out of each one of these guys. Take 1 out of here, and you have to take 1 out of each of these guys. I didn't live too close. Take 1 out of here, and you take 1 out of here. Oh, and look at that. 1 out of 4. Put that together, you got yourself another 5. Now we got, oh, that's a group of 4, that's a group of 4, group of 4, group of 4, group of 4. This because this came from a different division. Give him back to the rest. And we got, look at that, 5 groups of 5. That is induction of mathematics and arithmetic. That's, you just get yourself some rocks. Okay? Let's do geometry while we're at it, okay? Because we're on a roll here. We already knocked out addition, subtraction, multiplication, division. Did I say that? Multiplication, division, addition, subtraction, fractions. Doing geometry. See, we kind of cheating because we got a grid here, but it wouldn't matter if I had sand. If I had a little Zen garden going on here, I would still do this because I'm autistic. And I would line up my rocks. Do. Look at this. You see it? There's a pattern. There's a pattern going on. So, you can see that from the spacing of squares, inside the triangle, it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Ha 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 ha. Ha 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 ha. Pretty cool. Now, notice something though. I were to, let's just get rid of these guys. See how these guys are spaced out? If we were to try to keep this spacing, but like convert it sideways. You know what I mean? Such that these guys, let's fill these guys with their spacing. And these guys kept that spacing from before. Look at that. We have room for an extra rock here. Isn't that interesting? Internal, well, it's actually, in a sense, it's treating, say, these rocks as the outside. And if you were to put these ones here, you get that nice 5, 5, 5, but these squares are actually inside. All right? You're more looking to fill kind of this space up here. So if you make the spacing, hi Ridley. Did you see a mailman? Oh, good girl. What's up? What? You wanna go for a walk?
Okay. So we will do another exercise to demonstrate the inductive principles. Oh, he's going to leave. He doesn't want to hear about the math. Okay. Let us do another little exercise in the inductive steps of arithmetic. Let us start with a single unit. I will put here single unit, and I will put as a symbol the number 1 here. I will follow that up by putting 2 things here. I will put 1, and I will just count it out here. 2. And let us just keep going. 1, 2, 3. 1, 2, 3. 1, 2, 3. 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have a pattern. Look, a triangle. That triangle also goes not just 1, 1, 1, but if you were to put it the other way, 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 1, 2, 1. 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Wow! Look at that. 2, 3, 4, 5. Five by 5 triangle. Inductions. We can make a square. Look, we're going to need one more. Square. We can also make other shapes. Let's see here. 1, 2. And then let's go 1, 2 sideways. And then we'll do 2 down. And then 2 sideways. And then 2 flat. So now let's make this one longer. There, we got ourselves an octagon. Let's just draw this out here. We got 1, 2, 3, 4, 5, 6, 7, 8. Look at that. One, 2, 3, 4, 5, 6, 7. Let's not put a flat one this time. Just back to angles and then flat. Does that make sense? Did I need to even say anything? We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. All with rocks. How did I do it? By adding 1, 2 to one side, and then dividing those 2 into groups. One group that goes on the bottom, one group that goes on the top. In fact, we could say that the top and the bottom are like opposites. In fact, this pair and this pair are like opposites. And then this pair and this pair, and this pair and this pair are like opposites. And then this pair and this pair are opposites. We made them at 2 by 2. There are 8 sides. Took 2 rocks each. Let's do it over here so I don't have to erase that. 2 times 8. We could just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. Because that's 8 and 8. That's what that means. 8 and 8, which is the same as what is actually a bunch of ones. 8 of them, in fact, added together. Which would be then about 16 ones added together. It's quite self-explanatory. So, what else is there to say? 1, 2. How do we make 10? Let's try to make 10. 1, 2. Well, these guys have to we're going to shoot off here, but instead of making another set, we'd have to just kind of angle them a bit less. So it's a corner. And then that's 45, and then a base. We have to basically make a circle, in fact. In fact, the more rocks I add to try to make a multi-sided object, the more circular it gets. And so, in fact, let's just call this a circle. Look at that. A circle is such that if I were to put a rock here, that rock would be about an equal distance from this rock, as it is from this rock, as it is from this rock, as it is from this rock, or this one, or this one, or this one, or this one, or this, or this, or this, or this, or this, or this. That's what makes it a circle. Look at us go. We are flying through inductions here.
Okay, so I got really bored of doing inductions in basic arithmetic, so I set up here a double slit experiment instead, so that we can do something inductive that's actually way more fun than doing arithmetic, because we're not children. So here's a laser pointer, and if I put that, you can see it's on. I'm not going to point it at the camera. And we have it face, this direction. You can see it sets up over there. Okay. If I move these in front of our, you can see it even reflects. Ooh. Ooh. And you can see her. Oh, look at that. It's doing a little. So, got that set up. got some razors from a glass cutter, and there's from a shaving kit. There's actually a little wire between that pair there. You can see there. So that's my double slit, and it works like this. Okay, beautiful. Look at that. So this is a single slit. I will just turn it to a single dot. So there's the dot. That's just the laser pointer pointing at the wall. So it is just a stream of coherent light moving in one direction, and then we will pass it through a single slit. So coming up on the slit here. There we go. Look at that. Beautiful. Beautiful. So that's our single slit interference. Disperses, I guess you can't really see my hand. You can see it when I block the light. How we are getting this pattern that stretches across. Okay, so I am now going to do the double slit, and we will see a similar but different pattern. So single, back to nothing, coming up on the double, and there's the double. Let's see if I can get this a bit. Oh, the camera's in the way here. There we go. Look at that. Look at that. That is a double slit. So the first primary light is still here, but there's this interference pattern as it gets darker and darker. It gets really dark here, nothing here. And then we get this spot. It's just on my hand. It's just, oh, I can move it over here. Look at that. This second spot of light that projects onto this wall. Isn't that cool? Look at that. So this stream here, that's on my hand, closer to the camera, is the interference pattern light of the double slit. Now that the camera's out of the way, I'll just play with it a little bit. Maybe even back this up a bit so you can kind of see it stretch across the wall. And send that light off. Isn't that cool? You can kind of see the second pattern also has a splitting effect. Let's see if I can zoom in on it. How it keeps up that pattern. Change the lighting a little bit here. Just changing the camera lighting. There's nothing to do with the experiment. Look at that. Isn't that beautiful?